potential energy. Yeah. Okay, now let's do a quick recall on what is gravitational potential energy. All right, and how to calculate it. What is the things that can be calculated in this subtopic? Okay, so the gravitational potential energy. There are two things that we need to calculate in this subtopic. So first, first the things that we are going to calculate, of course, is the gravitational potential energy. So we need to know what does it mean by gravitational potential energy. So let's say now you have a planet, all right, and this planet there's a gravitational field around it. Okay, so a gravitational field is around it, and anything that you place inside this gravitational field, it will experience gravitational force. So let's assume initially there's nothing inside this gravitational field, and what happened is that now you're bringing something from outside this gravitational field. Let's say this is the original positions of the object. You bring it into the gravitational field. Okay, you bring it from, okay, let's say this is r equals to infinity. You bring it from infinity into a field, okay, at a point in the field, so that the distance between the object and this blue color object is equals to r. So now in this case, okay, the first thing that we have to know, this red color object, this is what we call point mass, which is initially is already in the system and you are not moving it, and then you move the blue color particles, okay, this blue color mass, which we call test mass, from infinity into a point inside the field of the point mass. Okay, so this test mass, you bring it, you place it inside the field, and the distance between point mass and test mass is now equals to r. And when you place the blue color, which is the test mass, inside this field, they will then experience the gravitational force. Okay, so the work done to bring the test mass from infinity to point r, we calculate it by using u equals to negative gmm over r, where capital letter M is the point mass and a small letter m is the test mass. All right, so you bring it from infinity, you place it inside the field, and this is the amount of work need to be done in order to move the charge from infinity into the field. Now, sometimes you don't have to move it from infinity. Sometimes maybe the charge is already in the field. Okay, so this is positions 1. And then you bring it, okay, let's say you bring it to here. This is a positions 2. All right. Then what happened is that now you are not bringing it from infinity, which means you have two gravitational potential energy. The first potential energy is coming from point 1, okay, where you're considering the work done to bring it from infinity to point 1 and the work done to bring it from infinity to point 2, and then you subtract them. So in that case, what do we have? Okay, we have a u, which is a change in gravitational potential energy from 1 to 2, which is equals to u2 minus u1. Right? And then the equations, when you expand it, it becomes negative gmm bracket 1 over r2 minus 1 over r1. So final minus initial r. Okay, and remember the r is not the r between object 1 and 2. It is the r from object 1 to the point mass and object 2 to the point mass. Okay, so basically you're looking at this r. So from object 1 until point mass, this is your r1. From object 2 until point mass, this is your r2. Which means if you move another object along the same orbit, then no work need to be done. Okay, if the r is equal. So if r1 is equals to r2, then no work done. Okay, then the delta u is equals to 0. All right, because the things that we're looking at is the r. Okay, r is the things that affects the work done. So if you are bringing it to move along the same orbit, then no works need to be done. Okay, now let's go back to the questions. So questions 1 is just a very simple questions. Determines the gravitational potential energy of the Earth due to the moon. So now you have two objects, the Earth and the moon. So you want to calculate the gravitational potential energy that needed to keep these two objects at a distance that is equal to 3.84 times 10 to the power of 5 km apart. All right, so initially the system is empty. Now you want to place these two objects inside the system. So what is the energy needed to be done? So simply calculate it by using U equals to G, and then so since we have two objects, the Earth and the Moon, so GME MM over REM. All right. So you plug in the value. Oh, I should have a negative here. So you plug in the value, then you will obtain, okay, this is your substitutions, then you will obtain negative 7.63. Negative 7.63 times 10 to the power of 28 joule. All right. And one thing you have to be careful is the unit. If you look at REM, the unit given is in terms of km. So you need to convert it into meter before you do the calculations. And for questions B now you're looking at the Earth and the Sun. Okay, so you want to find out what is the work need to be done to place these two objects in the system so that they are located at a 1.5 times 10 to the power of 11 meter apart. So you calculate it by using U equals to negative G. Now you have the Earth and the Sun. So GMEMS over RES. So this one, the R is a simple. Why? Because you are given the quantity in terms of meter already, which is SI unit. You don't have to convert it. But for the questions A, you need to convert the unit into SI unit. So again, so you do the substitutions and eventually you should obtain negative 5.32 times 10 to the power of 33 joule. Right? So this is the final answer. So now I give you 3 minutes to copy the answer, to write it down, and also the summary, okay, the revisions. So make sure you understand how many things can we calculate in this subtopic, okay, gravitational potential energy. So 3 minutes for you to write it down. If you have any questions, you may ask. All right. So next, let's look at questions number 2. So questions number 2 now, it involves the force of an object. So if a satellite of mass 800 kg falls from a height at 400 km to the surface of the Earth, what is the loss in gravitational potential energy? So how are we going to calculate these questions? Okay, now let's see. First, I would like you to sketch a diagram so that you can see what happens. All right. So initially, okay, initial position. Initially, what happened is that now you have the Earth, okay, and then the satellite is located, okay, is located at a position that is 400 km from the surface of the Earth. Okay, 400 km. But if you recall, okay, you recall the equations that we have learned so far, all of them, when it comes to r, we are going to use the distance from the center of the object. So if you sketch it out, then you will be able to see which r should be used. So you have to use this r. What does it mean? It means if you want to calculate r, then you need to take into considerations the radius of the Earth, okay, which is your RE. So which means for questions for initial position, okay, for satellite at 400 km above the Earth, when it comes to the calculations of gravitational potential energy, the R should be equals to RE plus 400 times 10 to the power of 3 meter. Because you are given km, you need to convert it into meter. And then how about its final position? Now it drops, okay, it drops onto the surface. So now your object is located on the surface. All right, it is located on the surface. So this is the center. So what does it mean? It means the r that you're going to use is simply just re, because now it's located on the surface, so you don't have to add anything. So in this case, r is straight away equals to re. So we have two different r, one for initial positions and one for final position. It is always a good idea to sketch a simple diagram so that you can see what is the information given, so that you can see whether you're using the right informations in your calculations or not. So now question is asking for the loss in gravitational potential energy. Now, what does it mean by the loss in gravitational potential energy? Well, it simply means it's asking for delta U. All right, delta U, the change. So loss means there are some changes happen in our system. So we are looking at the change in the gravitational potential energy, which is negative GMM, and then bracket 1 over R final minus 1 over R initial. All right. So given R, okay, capital letter R is actually your mass of the Earth, your ME, because that is your test mass, the mass that is not moving. And then the small letter M is your satellite, the M's of the satellite, which is equals to 800 kg. Okay, it is a test mass. So therefore, we use it as a small letter m. So it is equals to negative. Now I leave it to you. You yourself substitute the value. So I'm just going to show you what should you put in the r. So 1 over, now r final is re. Therefore, re here minus 1 over, now r initial. R initial we have re plus 4 times 10 to the power of 3 km. So this is the R that you should use in the calculations. So you sub the value here, you sub everything into the equations, and eventually you should obtain negative 2.95 times 10 to the power of 9 joule. Okay, times 10 to the power of 9 joule. So this is how you solve these questions. So now I give you 2 minutes to write down the solutions and also to sketch the diagram in your books. Make sure to include the diagram in the book so that you have a clue. You can imagine what is going on. How does it happen? All right, so you have something from 400 km above the surface, and then it drops onto the surface. All right, it drops onto the surface. So 2 minutes for you to write it down and also to sketch the diagram. Copy these diagrams into your books. Okay, copy the diagram. All right. Okay, so make sure you understand what is the difference between first and second questions, because that is the only questions that can be asked in this subtopic. All right, as long as you don't make any mistake in determining the R, then you should be safe in chapter 7. Chapter 7, actually, the question is very straightforward. All right, the only issue is how to determine R. If you got the wrong R, then basically the whole questions, you cannot answer it. You cannot get it right already. All right, because almost every questions in chapter 7, you need the radius. Okay, you need the distance, the R, in your calculations. So if you can determine, you can get the right R, then basically you won't be able to answer it. Okay. All right. Wait. Yeah. Okay. Now let's look at these questions. The moon has a mass of 7.35 times 10 to the power of 22 kg and a radius. Now, if you notice, you are given the quantity, the unit in terms of km again. Okay, in terms of km again. So now when it comes to km, then you have to be careful, all right, because you need to convert it into meter. Okay, what we need is just a meter. So this is the types of questions that you will get in chapter 7. Just one statement. Okay, nothing. That's why I say it's easy, because it's very straightforward. All right, so you have an object which is moon, and the mass is 7.35 kg times 10 to the power of 22, and the radius is 1740 km. Determines the gravitational field strength. So first of all, you need to understand what is gravitational field strength. That is our AG. Okay, now when it comes to a gravitational field strength, okay, I want you to take note. Some books, they like to use symbol G, but for me, I like to keep it. I like to keep the symbol AG. Why? Because when you use G, in your mindset, you already think it is always equals to 9.81, which in fact is not. It depends on the planet. Okay, so for me personally, I like to use AG so that you won't get confused between AG and G. All right, between AG and G. So some of the books, they like to use G. It doesn't mean that they are wrong. They are correct as long as you put a subscript. But when it comes to students, okay, because of your well, I would say your impressions. Okay, whenever you have G, you always thought that it is equal to 9.81. That's why in my lesson, I avoid using G in my calculations. I stick to original symbol, which is AG. All right, I stick to original symbol, AG. So it doesn't mean that I'm wrong, or other videos or other books, they are wrong. All right, just that we have own preference. So it determines the gravitational field strength at the surface. Now you want to calculate AG. So what is the equations of AG? AG equals to GM over R squared. All right, so we have these equations. And then, well, basically we have everything's already. Okay, we have the mass, and now we have the R in the questions. So you plug it in, make sure everything is in terms of SI unit. Then you should obtain 1.62 and kg minus 1. All right, and kg minus 1. Okay, now, next one. Okay, next one is a probe of mass 100 kg is dropped from a height of 1 km. Now, you see, the question is same as the previous questions, the question number 2. All right, just that they change the object that is dropping from far, and they change the height of the object. So now you have a probe of mass 100 kg is dropped from a height 1 km onto the moon's surface. So calculate the change in the gravitational potential energy. So what is the things that we have right now? Okay, now we have the moon, and then the probe is 1 km above the moon. Okay, so this is your 1 km. So remember, when it comes to calculations, the information that we need to use in our calculation is from the center of the mass, of the point mass, until the probe. So this is the R. So you need to take into considerations the R moon. Okay, so initial state, at initial position, initial state, your R is equals to RE plus 1 km, which is 1 times 10 to the power of 3 meter. Okay, 1 times 10 to the power of 3 meter. So when it comes to a final state, so final steps, now it drops onto the surface. So again, now you have a final, so you have the moons, and then now it's on the surface. All right, so the R is simply equals to the radius of the moon. Okay, so now you have R equals, oh, it's the moon. Okay, R equals to Rm. So the change in gravitational potential energy, again, you're just going to use the same equation, which is delta U equals to negative GMM bracket 1 over R final minus 1 over R initial. Okay, so you try to solve it by yourself and you should obtain negative 1.62 times 10 to the power of negative 5 joule. All right, so I give you 2 minutes to write down these two questions before I move on to the next questions. Next questions involve the conservations of energy. All right, so we finish these two sub question first before we proceed to question C. So again, 2 minutes for you to write it down. Remember to sketch a simple diagram in your answer. All right, so that you can see why my R is equals to Rm plus 1 km. Why my R is equals to just Rm at the final state. Okay, the reasons why. So in our class, we focus on why. Okay, why we want to use this value, why we want to use that value. Okay, so you sketch the diagram. Okay, so write it down, then we'll discuss next questions. All right, so question C. Now, question C, if all the gravitational potential energy lost is being converted into kinetic energy, okay, so calculate the speed at which the prop hits the surface. So now you want the final speed. So what happens right now is now you have a moon's here. So initially it's located at 1 km above the moon, all right? So this is 1 km. So what happens at initial position? Initially, U is equals to 0 ms negative 1. All right, that's why in the previous questions, it uses the terms drops. All right, so initially, is U equals to 0 ms negative 1, and then it start to drops until it hits onto the surface. All right, where now you want to determine the V. So V is an unknown value. Okay, so this is initial. Oops. Initial positions, and then this is the final positions. So what we want to do right now, we want to determine the value. All right, we want to determine the value, but how? If you look at the question, it tells you all gravitational energy loss is being converted into kinetic energy. And we know in energy is always conserved. All right, When we look at energy, they're always conserved. So which means in this case, if there's no external force, there's no other energy loss, then we can then assume summation U is summations pula delta U is equal to delta K. The change in gravitational potential energy is equal to the change in kinetic energy, which means all of the potential energy has been transformed into kinetic energy. All right, because we assume there's no other energy loss. There's no other external factor that will affect the movement of this probe. So delta U is equal to delta K. And when it comes to delta U, now we don't have to include the negative sign. All right, negative sign in previous question, it just tells us whether it's work done on the system or work done by the system. Now we just want the magnitude. So we are going to put 1.62 times 10 to the power of negative 5. All right, because we just want to look at the amounts of energy. So 1.62 times 10 to the power of negative 5, it is equals to our kinetic energy. So 1 over 2 mv squared, it is equals to 1.62 times 10 to the power of negative 5. All right, so rearrange the equations. What are you going to get? You will obtain V is equals to negative 56.92 ms negative 1. Now, because you square root the value, so you will obtain a plus minus sign. So the correct answer actually it should be negative because something is dropping. When it is dropping, the direction is downwards. Okay. Now, if you look at the questions, why it gives you a positive final answer? Because the question is asking for speed. So when it comes to speed, then we need to write one more sentence. Okay, where now the speed is just the magnitude. So speed is 56.92 ms negative 1. Okay, without negative sign, because speed is just a magnitude without plus minus sign. So you obtain a final answer which is a negative value, then you rewrite it in a statement form, in a sentence form. All right. So now that is our answer for question C.
Madam,
Yeah.
yang max tu yang 100 tadi kan?
Yeah, mass should be the prop because now the object that is moving that involve the motions is the prop. Prop is dropping. Therefore, you see, I use small letter m in my calculation. Okay, good questions. So this m is our test mass because now it is a mass that is moving with kinetic energy that has motion. So 1 over 2 mv squared equals to 1.62 times 10 to the power of negative 5. All right, so against 2 minutes for you to write it down. So remember, this is our small letter m, 100 kg. Okay, so sendiri buat catatan ya, nilai apa yang diguna, M besar ke M kecil yang diguna di dalam setiap soalan. Itu pun penting di chapter 7. Okay, biasanya pelajar salah di R, pelajar salah di M. All right, now let's proceed to the next questions. So next question is escape velocity. All right, escape velocity, what you have to know is just that now you have two equations. one equations can be used at any positions above the surface of the planet, of the object. Okay, and another one, it must be on the surface. All right, so the first equation is at any position. Okay, at any position above the surface, then we use equations V. Now, we use a subscript E, okay, to indicate that now this is an escape velocity. So it is equals to square root 2gm over r. So if you look at the equations, now this equation, they uses a capital letter M. So which means the mass of the dropping object, of the test mass, of the object that want to escape from the earth, from the space, okay, it doesn't matter. All right. So another one is on the surface. So on the surface, the informations that we're going to use, the equations that we're going to use is straight away equals to square root 2gr. So again, if you look at these equations, they all uses the information from point mass. Okay, none of them is from the test mass. So which means the object that is escaping from the universe, okay, is it doesn't matter the mass. So it's either right, it doesn't matter whether it's you or maybe it's a satellite that wants to escape from the, for example, from the Earth. Okay, both of them, they are going to need the same escape velocity, regardless of the mass of the test mass. Okay, tak kisah kamu ke satellite ke yang beribu-ribu kg itu ke, yang mana satu nak escape daripada kita punya planet, kita punya Earth, okay, dia tetap akan guna equations yang sama, nilai yang sama, escape velocity yang sama. So test mass actually is not really important in this subtopic escape velocity. All right, it's just an object that want to escape. Okay, the question just give you an object so that you know what is going on. Okay, so questions A, calculate the escape speed from the Earth's surface for a rocket that is mass 3,000 kg. So for instance, this 3,000 kg is not needed in questions A, because if you look at my equations, okay, it's either capital letter M, which is the mass of a point mass, or capital letter R, another equation, which is the radius of the planet. Okay, radius of the Earth. So this is our equations. So for these questions, which ones we want to use? So it is from the surface. So it's up to you. You want to use any equation. Okay, so the first one is for any equations, any position. The second one is solely for on the Earth. So let's see if we want to use the second equations. So VE equals to square root 2gr. So now you're looking at the Earth. All right, at the Earth. Therefore, square root 2, now G is 9.81 because we know that is constant value, times with the R of the Earth, which is 6.4 times 10 to the power of 6. Straight away, you will obtain 1.12 times 10 to the power of 4, m as negative 1. Okay, so this is the answer for questions A. Okay, the answer for questions A. Now, when it comes to questions B, so how to solve questions B? Determines the kinetic energy of the rocket in part A that it must have at the Earth's surface in order to move infinitely far away from the Earth. Right? So how are we going to solve it? So when it comes to these questions, all right, because now you want it to move away, okay, you want it to move infinitely far away, so you want to look at its final velocity. So straight away, K is equals to 1 over 2 mve squared. So this is the energy needed for it to escape from the surface of the Earth. All right, so you use escape velocity, so 1 over 2. Now this mass, because the object that is moving, once again, is the rocket, okay, rocket that is moving. So this one, we use the mass for a rocket, right, which is 3,000 kg. Okay, 3,000 kg. And then escape velocity, 1.12 times 10 to the power 4 squared, which is equals to 1.88 times 10 to the power of 11 joule. So this is the amount of energy needed. So energy needed, it depends on the object. All right, if you have an object with a large mass, then you use a very large mass, you need more energy. But if you have an object with a small mass, then you use just a bit of energy to move it. Okay, but then when it comes to escape velocity, the escape velocity is still the same. It doesn't matter whether you're looking at rocket or you yourself want to escape from the Earth. Okay, so now let's say you want to escape, Ali want to escape from the Earth. the escape velocity is still 1.12 times 10 to the power 4 meter per second. But when it comes to energy, then you need to calculate the new energy. All right. So maybe less energy needed because the velocity is 1.12 times 10 to the power 4. All right. Because your K is directly proportional to M. So if Ali want to escape from the Earth, then less energy is needed. All right. So this is how we solve it. All right. This is how we solve it. So any questions? I heard someone switch on the microphones. Anything you want to ask? All right, if no, I give you 2 minutes to write it down. All right, 2 minutes to write it down, including the summary on the right-hand side. All right, make sure you know which equation is for which situations. And the questions A, if you want, you can calculate, you can use both equations to see whether both of them give you the right answer or not, give you the same answer or not. Okay, questions A can be solved by either one equations. Okay, kedua-dua equations boleh diguna pakai untuk jawab soalan A. Okay, so 2 minutes for you to write it down. If you want to try questions A for another equations, go ahead. Okay, that would be the best so that you can see how and when to use them. Okay, so 2 minutes, Salin, and then we have a last questions for today's lesson. All right, let's proceed to the last questions. Last questions. A projectile is fired vertically from the Earth's surface with an initial speed. Okay, now you're given an initial speed 10 km per second. Now km you're given. So neglecting air resistance, how far above the surface of the Earth will it go? So now we have the Earth, and then you have a projectile. So let's say now your object is located here. So initial speed u, it is equals to 10 km as -1. Okay, and then you want to find out what is the final height that it can go. What is the h? All right, and then now if you look at these questions, actually there's a piece of hidden information. How far above, which means it is talking about maximum height. So what happens at maximum height? At maximum height, our v is equal to 0 m as -1. All right. So initial state, we have initial velocity. Final state, our velocity is equal to 0. Okay, so now let us see how are we going to solve it. Now it involves height and it involves velocity. So which means in order to solve this question, it will be best to use conservations of energy concept to solve it. So summations E initial equals to summations E final. When you expand the equations, all right, you will have U initial plus K initial equals to U final plus K final. All right, so that is the information that we have right now. Rearrange the equations. Oops, final. Okay, rearrange the equations, but before rearrange it, we can remove k first. Okay, you can remove the k final. Why? Because your final velocity is equals to 0. Okay, that is what happens at maximum height. So rearrange the equations. Okay, we will have a k initials equals to uf minus ui. Okay, uf minus ui. So this is actually your delta u. So now from this step, we can then expand the equations. So 1 over 2 mu squared, it is equals to negative g m capital letter M and small letter m. And then bracket 1 over r final minus 1 over r initial. Aha, now this is the part where you have to be careful. So what is your r initial? R initial object is on the surface. So it simply equals to the radius of the earth. All right. So r final, what do we have? We have r plus h. Okay, r plus h. And when you look at these equations, you are not given the mass of the projectile. But when you look at the equations, now you have small letter m on both sides. So you can cancel it out. Okay, you can cancel it out. And then with r initial equals to r final equals to r plus h, you sub everything into the equation, and eventually you will obtain h equals to 2.55 times 10 to the power 7 meter. All right. So substitutions, I leave it to you. Okay, you learn how to do the substitutions and the rearranging equations. All right, so you tried it until you get a final answer. And if you got a final answer, no questions, then you may leave the class. That's all for today. Okay, that's all for today. So I will stop at these questions. Next questions, which is next subtopic, which is a satellite. Okay, we'll keep it for next lesson. Okay, satellite, we keep it for next lesson. This one, you write it down and then make sure you complete it. You do the rearranging. Okay, you rearrange the equations, you do the substitution and so on until you get a final answer. Once you obtain the final answer, then you may leave the class.